Hello everyone. Welcome back to our channel. Microsoft recently announced the Mayorana 1 quantum computing chip for use in their quantum computer. Just a few months earlier, in December 2024, Microsoft's rival Google had announced their quantum chip called Willow. Google's chip is considered to be a major milestone on the road to the future of computing. The Willow QPU, or Quantum Processing Unit, is key to Google's plans to build a scaled-up quantum computer, a piece of tech that has the potential to solve much more complicated problems than classical computers. Google claims that Willow was able to complete one particular problem in 5 minutes, while the same task would have taken today's supercomputers 10 septillion years to finish. That is 10 raised to the power of 25 years to finish the task. This is much larger than the estimated 10 raised to the power of 23 number of stars in the observable universe. It's much larger than the number of grains of sand on Earth, estimated at around 10 raised to the power of 20, and it's almost the same as the number of atoms in a human body, which is around 10 raised to the power of 27. Soon after Willow's release, Microsoft shot back with their quantum chip, the Mayorana 1, in early February 2025. There is no doubt left that after these announcements one after another, we are witnessing a race for quantum supremacy between two of the most well-funded tech giants. This video is in 3 parts. In part 1, we'll briefly explain what quantum computing actually is and how quantum computers are different from classical computers or regular computing that we have become so used to and also have made so much progress in the past 60 years or so. The goal is to break down the mystery of quantum computing and provide a fairly detailed overview of this exciting and rapidly evolving technology, which includes what is it that quantum computers can actually do. In part 2, we'll explore the quantum computing strategies of the two most funded and advanced tech giants, Microsoft and Google. We'll shed light on their quantum chips and do a detailed comparison of their technology, advantages, and disadvantages. In part 3, we'll go over the potential applications of quantum computers, the impact of quantum computing technology on human life and our planet, and what are the potential consequences of quantum computing on the future of humanity. We've heard of technological singularity, that hypothetical point where AI surpasses human intelligence, possibly leading to an unpredictable explosion of knowledge. It's the moment where quantum AI systems become the primary drivers of progress, outpacing human ability to comprehend or control. Renowned futurist Ray Kurzweil and many other experts have talked extensively on the implications of singularity, ranging from unprecedented advancements, new ethical, philosophical, and existential challenges. Now, throw quantum computing into the mix, and this singularity isn't just about being smarter, but tapping into the very essence of reality itself. Quantum singularity is a point of no return for mankind, potentially cohabitation with entities that blend the mysterious quantum realm with machine intelligence and parallel universes. So let's begin with part 1. Quantum computing involves quantum theory, a set of physics principles that govern the behavior of matter and energy on a subatomic level. Unlike classical physics, which describes the behavior of macroscopic and large objects that we see in our daily life, quantum theory deals with the behavior of particles that are incredibly tiny and small and often behave in ways that seem mysterious and counterintuitive. We call this world of invisible particles, such as atoms, protons, electrons, photons, etc., the quantum world. Okay, so let's compare classical computers, our everyday computers that we use today, to quantum computers. Classical computers use bits, using binary language represented as ones and zeros by the states of transistors, which function like light switches. The CPU, made of these transistors, processes data using logic gates. The state of a classical bit can be either on or off. That is, it can only be in one of those two states. Another example is that if you take a coin and flip it in the air, it will spin, and when it lands on the ground, it can be either heads or tails. Unlike classical computers, which use bits to represent information as either 0 or 1, quantum computers work with qubits or quantum bits. Qubits can exist in multiple states simultaneously due to quantum properties like superposition and entanglement. In superposition, qubits can represent both 0 and 1 at the same time. To visualize this, consider a coin toss. While a classical bit must be either heads or tails, a qubit in superposition is like a spinning coin that exists as both heads and tails simultaneously. This property empowers quantum computers to process multiple possibilities in parallel, allowing them to explore a vastly larger computational space than classical computers, which process information sequentially. The phenomenon of superposition enables quantum computers to perform certain calculations exponentially faster than even the most powerful classical supercomputers. solving problems that might otherwise take millions of years to complete. Before we step further, let's understand the core principles of quantum theory that include superposition, entanglement, the uncertainty principle, and probability distribution, measurement, and decoherence. We'll try to explain these concepts in a simple manner. First, let's take superposition. Superposition is the idea that particles can exist in multiple states simultaneously. For example, a particle, or qubit, can be in two different positions or spin at the same time. That is, it can be spin up and spin down simultaneously. This principle that a qubit can exist in multiple states simultaneously allows quantum computers to perform many calculations in parallel and at once. Next core principle of the quantum world is entanglement. Entanglement in quantum theory is a phenomenon where two particles become linked in such a way that their states become dependent on each other. The changes in the state of one particle can instantaneously affect the state of the other, no matter how far apart they are. This happens faster than the speed of light and allows for instant communication and computation regardless of the distance. There are only two known situations or phenomenons which break the speed of light rule. One is the messages exchanged through entanglement of particles, and the second is the speed at which our universe is expanding. Everything else besides these two follow the rule that nothing can travel faster than the speed of light. The third principle is the uncertainty principle, formulated by physicist Werner Heisenberg. This states that the position and momentum of a particle cannot be precisely measured simultaneously. While this principle is fundamental to quantum mechanics, it's distinct from the wave function and amplitudes that form the core of quantum computing. In quantum computing, before we measure a qubit, it exists in a superposition state. This can be thought of as a quantum probability distribution, where each qubit has a complex amplitude, not just a probability, for being 0 and an amplitude for being 1. These amplitudes are represented mathematically as coefficients in the qubit's quantum state. For a quantum computer to provide useful output, we must measure the qubits, which causes the quantum system to collapse into a classical state. This measurement yields a specific outcome, 0 or 1, with a probability determined by the square of the amplitude's magnitude. After measurement, the qubit loses its superposition and behaves like a classical bit. This measurement-induced collapse has crucial implications for quantum computing. The delicate nature of quantum states means that unintended interactions with the environment can cause premature measurement-like effects, potentially disrupting quantum computations. This is why quantum computers require extensive error correction and isolation from environmental interference. The unintended interactions of a qubit with the environment is called decoherence. Decoherence occurs when a qubit in superposition interacts with its environment, causing the quantum information to leak out into the surroundings. This interaction entangles the quantum system with countless environmental particles, effectively transforming what was a pure quantum state into a classical-looking mixture. Quantum superpositions collapse into definite classical states due to decoherence. Decoherence isn't the same as measurement in quantum mechanics, though both cause wave function collapse. For quantum objects, decoherence happens gradually through environmental interaction, while measurement is an intentional, discrete event. For extremely large objects, decoherence happens extremely rapidly, which is why we don't observe cats being both alive and dead simultaneously as portrayed by the Schrödinger's dead and alive cat experiment example. Decoherence is one of the main challenges in building quantum computers. Quantum information is incredibly fragile and easily disrupted by thermal vibrations, electromagnetic radiation, or any interaction with the environment. Quantum computers must be heavily shielded and cooled to near absolute zero to make qubits last as long as possible and minimize decoherence. Even with all these precautions, qubits typically maintain their quantum states for only microseconds or milliseconds before decoherence occurs. If you put a qubit from the 0 state to the 1 state and wait 100 microseconds or 200 microseconds, at some point that extra bit of energy will decay out of the qubit. Coherence time is how long quantum information lasts inside of a qubit and is one of the metrics used to assess the quality of the quantum computer. We know how classical computations work, but how do quantum computers really work? Let's explain the difference between the two. We'll use the two outermost electrons of a phosphorus atom as qubits in our example. For classical computing, we have these two electrons represent bits. So each electron can either be represented as a 0 or a 1. As such, there are 4 possible combinations or states we can get at most from these two electrons. Thinking in terms of 2 bits of a classical computer, we can write these combinations as 00, 01, 10, 11. That is a total of 4 combinations that we get from 2 bits of information. To determine which one of the four combinations we have in our computer code, we have to provide two numbers to find the information. That is, we need to know the value of the first bit and the value of the second bit. If we increase the number of bits to 3, we will get 8 different combinations, or 8 different states, and we have to provide 3 numbers to determine which value we have in our computer. Now let's see how a quantum computer works when we use the principles of quantum mechanics that we talked about earlier: superposition, entanglement, and the uncertainty principle. It's important to note that there are a number of physical objects that can be used as qubits: photons, nucleus of atoms, electrons, or superconducting circuits, and in all cases their manipulation is key to quantum computations. For our qubits example, let's use the same 2 outermost electrons of a phosphorus atom. Since qubits, being a quantum objects, can be in both states at once or in a quantum superposition, we'll use coefficients to indicate the relative probability of finding each of the qubit in one state or the other. So we can think about each qubit as a wave of probability, and quantum mechanics allows us to create superpositions of each one of the 4 states that we have in our classical bits example: 0, 0, 0, 1, 1, 0, 1, 1. We can thus write a quantum mechanical state that is some coefficient times the number 0, 0, some coefficient times the number 0, 1, and so on. To determine the state of this 2-spin system, we now need to provide 4 numbers, or 4 coefficients. Whereas in the classical example of the 2 bits, we only needed to provide 2 numbers. If we add another qubit, we need to provide 8 different numbers to define the state of the 3-spin system, whereas in classical computation, it is just 3 bits. Now imagine that we have a 10-qubit quantum computer. That computer could store 2 to the 10th power values in parallel to describe this entangled configuration. With a classical computer, we would need 2 kilobytes or 16,000 bits. If we expand to a system with 500 entangled qubits, we would require more classical bits than there are atoms in the known universe. If we keep going, what we will find is that the amount of equivalent classical information contained by n qubits is 2 to the power n classical bits. To summarize, here is a comparison refreshed in a summary form. Classical computing calculates with bits and transistors, which can represent either 0 or 1. The power increases in a 1-to-1 relationship with the number of bits and transistors. Classical computers have low error rates and can operate at room temperature. Most everyday processing is best handled by classical computers. On the other hand, quantum computing calculates with qubits, which can represent 0 and 1 at the same time. Power increases exponentially in proportion to the number of qubits. Quantum computers have high error rates and need to be kept ultra-cold. They are well suited for tasks like optimization problems, data analysis, and simulations. So far we've talked about quantum mechanical principles and the mysterious behavior of qubits as it relates to their use for quantum computing. But what is it, and what can quantum computers actually do? Why is there such a hype around them? Well, it turns out that there are several things that quantum computers excel in, and there are quantum algorithms already being used to do or can theoretically perform these functions. There is a common misunderstanding that quantum computers are faster than classical computers. Quantum computers are not universally faster for every operation. In fact, most operations might be slower than those on your desktop computer. If someone just wants to watch a video in high definition or browse the internet or write a lengthy document in a word processor, quantum computers are not going to give any improvement over classical computers. Quantum computers are well suited only for certain kinds of challenges, like probability problems, optimization problems, such as instantly finding the best possible travel route, and other similar problems. The advantage of quantum computing lies in the significantly reduced number of operations needed to achieve a result, not in the speed of each individual operation. It is also crucial to design quantum logic operations in a way that the final computational result is measurable. The end result of a quantum computation should not be a complex superposition of states, as extremely complex superposition may not be measurable. Instead, the outcome should be a distinct state. This requirement is not trivial and requires extremely creative, difficult, and genius algorithms that excel in exploiting quantum superpositions for enabling computational parallelism for calculations that classical computers would take months and even years to solve. Quantum computing, though still in its early stages, has seen the development of some key algorithms that demonstrate the potential of this technology, but we are nowhere close to the type of algorithms that artificial intelligence would be able to develop. As of yet, we don't necessarily have the level of maturity nor the ultimate substrate or quantum computers that can massively scale, but here are a few main and relatively mature algorithms and their uses developed by humans for quantum computing so far. 1. Number factoring. Quantum computers can efficiently factor large numbers using Shor's algorithm. which has profound implications for cryptography. Most modern encryption relies on the difficulty of factoring large numbers. For example, RSA encryption, which is used in secure communications, digital signatures, and e-commerce, could be broken by quantum computers, necessitating a shift to quantum-resistant cryptographic methods. This capability affects everything from national security to personal banking security. 2. Quantum simulation. Quantum computers can simulate quantum mechanical systems far more efficiently than classical computers. This enables modeling of complex molecules, proteins, and materials at the atomic level. Practical applications include designing new pharmaceuticals by simulating protein folding, developing more efficient catalysts for industrial processes, and creating novel materials with specific properties. For example, quantum simulations could accelerate the discovery of room-temperature superconductors or more efficient batteries. 3. Complex optimization. Quantum computers excel at solving optimization problems with many variables and constraints. This includes logistics challenges, like routing delivery vehicles optimally across thousands of destinations, financial portfolio optimization, and improving manufacturing processes. In AI, quantum computers could potentially optimize neural network weights much faster than classical training methods, drastically reducing training time for large models from weeks to hours or even minutes. 4. Unstructured search. Through algorithms like Grover's algorithm, quantum computers can search unsorted databases quadratically faster than classical computers. This has applications in database searching, pattern recognition, and even in breaking symmetric encryption. For example, searching through massive genomic databases to find specific genetic patterns, scanning astronomical data for specific celestial phenomena, or rapidly searching through security footage for specific events. 5. Linear systems. Quantum computers can solve large systems of linear equations exponentially faster than classical computers using the HHL algorithm. This capability is valuable for computational fluid dynamics, for climate modeling or aerodynamics, structural analysis in engineering, and economic modeling. For instance, quantum computers could enable more accurate weather prediction by processing complex atmospheric data more efficiently. 6. AI model training in parallel. Quantum computers can potentially process multiple training scenarios simultaneously through superposition, dramatically accelerating machine learning. This could enable training on vastly larger datasets or with more complex models than currently possible. Applications include real-time language translation with perfect context understanding, medical image analysis with unprecedented accuracy, or fully personalized education systems that adapt precisely to individual learning patterns. 7. Blockchain and cryptographic applications. While quantum computers threaten current cryptographic methods, they also enable quantum cryptography, like quantum key distribution, which offers theoretically unbreakable encryption. For blockchain, quantum-resistant algorithms will be crucial, but quantum computing could also power more efficient consensus mechanisms and enable complex cross-chain transaction verification at scale. 8. Machine learning classification. Quantum versions of classification algorithms may significantly outperform classical approaches for certain problems. Applications include more accurate fraud detection in financial services, improved medical diagnostics from complex datasets, and better pattern recognition in security applications. For example, quantum machine learning could detect subtle market manipulation patterns invisible to classical algorithms. 9. Quantum sensing and metrology. Quantum computers can enhance precision measurements beyond classical limits. This enables more sensitive gravitational wave detection, improved GPS systems that don't rely on satellites, and medical imaging at unprecedented resolution. For instance, quantum-enhanced MRI could detect disease biomarkers at the cellular level without invasive procedures. 10. Drug discovery and development. Beyond basic molecular simulation, quantum computers could revolutionize the entire pharmaceutical pipeline. They could predict drug interactions, optimize formulations, and identify side effects before clinical trials. This might reduce the average 10-plus-year development cycle for new drugs to just a few years, bringing life-saving treatments to patients faster. 11. Climate modeling. Quantum computers could process the immense data sets needed for accurate climate prediction models, accounting for countless variables simultaneously. This would enable more precise projections of climate change impacts on specific regions, more effective carbon capture technologies, and optimal renewable energy deployment strategies tailored to local conditions. 12. Traffic flow optimization. Quantum algorithms could optimize real-time traffic flow across entire metropolitan areas, reducing congestion, pollution, and commute times. By simultaneously analyzing millions of vehicles, road conditions, and destination patterns, quantum-powered systems could dynamically adjust traffic light timing and suggested routes for maximum efficiency. The quantum AI revolution is almost upon us. It is a matter of years. Quantum computers will change everything, including our understanding of reality and human consciousness. The convergence of quantum computing and artificial intelligence represents a potential inflection point in human technological development. Together, these technologies promise to solve problems previously considered intractable, from discovering cures for age-related diseases that could extend human lifespan by decades, to creating perfectly efficient energy systems that could address climate change. They could revolutionize our understanding of the universe through simulations that model cosmic phenomena with unprecedented accuracy. For human welfare, these technologies might enable personalized healthcare that prevents disease before symptoms appear, economic models that eliminate poverty through optimal resource distribution, and educational systems that adapt perfectly to each individual's learning style. However, this revolution also brings profound challenges in privacy, security, and potential concentration of technological power. The coming decades will likely be defined not just by what these technologies can do, but by how societies choose to harness their capabilities for collective benefit while mitigating their risks. The quantum AI era may well represent humanity's greatest opportunity to solve our most pressing challenges, if we can wisely navigate its implementation. These algorithms provide a foundation for the ongoing development and showcase the diverse potential of quantum computers to tackle problems in cryptography, search and optimization, physics, chemistry, and other areas in ways that classical computers cannot. As both artificial intelligence and quantum technology continue to advance, undoubtedly new algorithms are likely to emerge, lifting the power of computational parallelism to unimaginable levels. Some pundits even go as far as unraveling the secrets of the universe, immortality, and life itself. This concludes part 1. Thanks for watching. Please stay tuned to our channel, as in part 2 of this video, we'll do a detailed comparison of the quantum computing strategies of Microsoft and Google. We'll shed light on their quantum chips and do a comprehensive analysis of their approach, architecture, technology, advantages, and disadvantages.